Okay, we're going to look at the 2.6 as an investigation, but I just kind of went through it on Desmos, and I just wanted to show you, just kind of run through it. It's just worthwhile just to watch it, because I just want to make sure that you get the main concepts. It's not very complicated, and so and the purpose of this isn't so much to graph; it's just to understand what the restrictions mean. So the first one is part A is looking at holes. So we get this function f of x that we want to simplify. When we simplify it, we notice that we can factor the top as a difference of squares, x minus 2, x plus 2. And then on the bottom we have x minus 2 as well. And so we saw from the previous lesson that we can cancel those x minus 2's, and we end up with just the fact that we have x plus 2. Now I didn't write that here, but we do have the restriction. I didn't really want to give it away, so I want to look at the graph. So the question asks you to graph the function prior to simplifying it. That doesn't mean it just means graph the top line. And so actually if you graph the top line, you get something like this, and it is just a straight line. It's a slope of 1 and a y-intercept of 2, and so you can see the straight line here. And that's just from Desmos. And then if you trace your cursor along the graph, what happens is you actually see that if you click on right around 2, and so I did that in Desmos and see what happens. If you click right around 2, what happens is the point shows up as a little hole, and so it shows you the coordinate 2 and then undefined. And so what happens is the shape of the graph doesn't change. It still stays like a straight line. It's just there's a little hole there saying that x cannot equal 2. And so that restriction comes from the bottom. We saw that in the last lesson, but we're just saying there's a little hole and such that x cannot equal 2. Okay? I would determine another rational function that simplifies to a polynomial with a hole at x equals 1 has a restriction that x cannot equal 1. And so we notice that all we have to do is make sure that we have an x minus 1 in the top and the bottom. So if x minus 1 is in the bottom and the top, we'll actually cancel out, and we note that we can use any function that will have an x minus 1 cancel out. If we draw the graph and see what happens at x equals 1, we can draw this graph, and the graph is actually just the x squared plus 3, so it's just an x squared plus 3 graph. And then if we trace our graph right around x equals 1, so right around there, we can see that the graph, again, it has a hole at x equals 1, and the point shows up 1 and undefined. And so if you do that in Desmos, you'll actually see you can trace your point all along this graph, and all the other points are defined. It's just that 1 is not. Now, if you're not clicking on it, you actually won't see it because the hole is it's really only defined at 2. At 1, at 1.000001, it is defined. And at 0.9999999, it is defined, but it's not defined at 1. So we'll never see it unless the computer's programmed to show it to you. And it's kind of nice that Desmos is programmed to show it to you. So part B is about asymptotes. We actually saw this in the last unit. It's really just a review. And if we graph 1 over x minus 3, we actually see this graph here, and it's just your reciprocal function shifted to the right 3. If we trace our graph near x equals 3 and see what happens, we actually see this, your point goes up and it just keeps going up forever and ever. And you'll notice that at 3.03 we're at 31, at 3.02 we're at way higher than that. And so we're actually the graph will approach, but we'll never reach this vertical asymptote. So there is a restriction at x cannot equal 3. But it's not a hole, it's a vertical asymptote. So we'll never actually hit x equals 3. From the equation that has 2 vertical asymptotes, it's kind of neat. We haven't seen this before. More so we care about the set up the equation than the graph in this unit. In grade 12 advanced functions, you do things like graphing these. But we'll just do them with the graphing calculator for now. If you want an asymptote at x equals 2 and x equals negative 1, we actually make those as restrictions. If we don't have anything on the top, they don't cancel out, so they do affect the shape of the graph. They're not holes, they are asymptotes. And what the graph looks like is at x equals 2, x equals -2, which is this line, we've got a vertical asymptote. X equals -1, we have a vertical asymptote. And then what happens is we approach that horizontal asymptote of 0, and we never actually ever hit x equals 2 and x equals -1, because you can't ever get there. You can't divide by 0. And so those are restrictions for this function. Okay, and those are called asymptotes. To summarize, what determines where a rational function has a hole? If there's a restriction that is not in the final answer, the restriction is canceled out, then it's a hole. If there's a restriction in the final simplified form, then it's a vertical asymptote. Okay, so very straightforward. Each of the restrictions can be classified either as holes or asymptotes, and it all just depends if they got canceled out or not. I determine the equation of a rational function that has both a vertical asymptote and a hole, so we come up with something that does cancel out, but then something that doesn't. And if we simplify that, we get 1 over x plus 1, which we kind of know what it looks like. It's the 1 over x graph shifted to the left 1. And that's what this is. But then the other restriction is x cannot equal 1. And so you've got this little point at x equals 1 where you have undefined. And so at x equals 1, you get undefined. At x equals -1, because the -1 is the restriction that does not get canceled out, that's the asymptote. Okay. Determine the equation of a rational function without any holes or vertical asymptotes. You can try your own. And this is kind of a challenging thing to do, but like we have to have something, a rational function, so some kind of algebra on the bottom, but we can't have a vertical asymptote, so we actually can't have any restrictions. So if there aren't any holes or asymptotes, there's no restrictions. We saw this in the previous lesson, but like what actually works is if you have a quadratic in the bottom that doesn't have any zeros. So this in the bottom is a quadratic shifted up 1. And you can shift it up however much you want. But as long as you shift the quadratic up, it doesn't have any zeros. So what it looks like is a little bell curve. Again, we'll talk about this more in advanced functions in grade 12, but like basically what we're looking at is at x equals 0, we've got 1 over 1, and then as x gets bigger, we just get 1 over 1 point something, and then 2, and it just gets smaller and smaller. So you can almost think about that, but we just graph that in Desmos, and Desmos shows us what's happening. Okay, so that's basically it for today.